Hi there. Want to talk a little bit today about some quantitative aspects of the things that we've been dealing with, phase diagrams and their solution calculations. We've been talking about intermolecular forces, and those relate to phase changes and to solutions, so we're going to deal with these quantitative aspects as well. So what we have here at the top in figure 1030 is a phase diagram. And the phase diagram, so what we have up here at the top is the phase diagram, and the phase diagram is a plot of temperature on the x-axis versus pressure on the y-axis, and the lines on the phase diagram show us where transitions occur, and on the line you have a equilibrium between the two phases, and so you can see that you have solid on the top on the left. If you increase the temperature, you melt and form a liquid, which is the purple region kind of in the middle. And if you continue to heat that, you vaporize and form a gas. If you cool a gas down at a temperature above what we're calling the triple point there, or rather at a pressure above the triple point, you condense the gas to a liquid, and if you continue cooling, it freezes to a solid. The triple point is the point at which you have solid, liquid, and gas in equilibrium, all three phases. Below the triple point, the solid can go directly from solid to gas and directly from gas to solid in sublimation and deposition. And that's not as unusual as you might think it is. We'll talk about one specific example that's pretty common. There's also a temperature up at the end of the liquid-gas line called the critical point, and the critical point is the point beyond which the distinction between gas and liquid kind of vanishes, and we get what's called a supercritical fluid, and we'll see a phase diagram with that laid out for us. Now, it doesn't probably look like this very much, but the nature of the intermolecular forces are what causes the shape of this diagram. So the one at the top, figure 1030, is one I'd classify as being kind of a normal one. And then if you look at the one right below it, which is unlabeled with a figure name, but it has the letter A on it, you probably can notice some difference there. So again, if we're looking at a phase diagram, the x-axis is temperature, the y-axis is pressure, and this phase diagram looks different, and the difference is due to the slope of this line here between the solid and the liquid phase right there. It's got a negative slope to it as opposed to a positive slope in the one above it. So this is what the phase diagram for water would look like. And if we're looking at water, 1 atmosphere pressure is a little above the triple point, and I'll try to draw a reasonable straight line across. I know I can't quite do it here. So if we start with really cold water at normal atmospheric pressure, of course it's a solid, and if we heat it up and we get to this point right here, what we see is that we have a liquid, and that point would be called the melting point if we were going up in temperature, and if we were going down in temperature, we call it the freezing point, and that's at 0 degrees Celsius, of course. If we go across on the liquid, eventually we reach the point where we have the liquid gas line, so this is gas over here, and that point, of course, is the 100 degrees Celsius, which is the boiling point of water, or the condensation point if you're going back in the other direction. So I've written T sub some letter there for melting, freezing, boiling, and condensation. If you cool water down, if you reduce the pressure enough, or as you start reducing the pressure, right, so if we go down here, which is a lower pressure, the freezing point goes up and the boiling point goes down. So you can have a lower boiling point at a lower pressure. That's kind of how a clothes dryer works. You pull a vacuum on the wet clothes, which reduces the pressure, and then heat it up, but you don't have to heat it all the way up to 100 degrees Fahrenheit because the boiling point is lower. That's also a technique that's used sometimes in organic chemistry to try and separate molecules that are hard to separate or that decompose at high temperatures, is to pull a vacuum on them and do a reduced pressure distillation. The next phase diagram is an unusual looking one. This is the carbon dioxide phase diagram, and again this is H2O. And we usually think of carbon dioxide as having that normal, positive slope of that solid liquid line there, as opposed to water's negative slope of the solid liquid line. And you have here this supercritical fluid region for CO2, which is the point you pass the critical point, which is right there. And a supercritical fluid of CO2 behaves differently from liquid CO2, which you don't generally see too much of liquid CO2. Notice the pressure scale here. These are really high pressures. This is what's called the log scale. So the first distance is a power of 10. The second exact same distance is a power of 10, but that means that in this case, this one's 90, this one's 900. And every time you go up, it goes up by a factor of 10. So the next gap is 9,000. So you have to read these very carefully if you have a log scale. The temperature appears to be linear, but that is something to note when you're reading those kind of graphs, is to look for those log scales. Now, when we're talking about the quantitative aspects of this, we're not going to talk too much about that. There's an equation that lets you calculate the new temperatures. We're probably not going to deal with that one too much in this course. It's a Clausius-Clapeyron equation. Basic concentration units I do want to touch on. These are all back in the chapter, let's see, the overview here. We say, I think it's chapter 4, maybe. There might be a different chapter where you have a basic review of those concentration units. Let's see, that figure came from another text, so I can't tell from that. You probably remember the concentration unit of molarity, which is symbolized by capital M, which is moles of solute per liters of solution. That's not liters of solvent, liters of solution, which may or may not be the same as liters of solvent. Molality is a new unit we use. It's got a lowercase m. It's moles solute over kilograms of solvent. So that's a very different unit. They can be kind of similar. I mean, if you're using a water solution, kilograms of solvent is going to be very close to the volume in liters of your solution. But in other cases, they might differ. The reason we use molality is that mass doesn't change as temperature changes, but volume does. Density is a function of temperature. So a solution's molality will change as we change its temperature. Its molarity will change as it changes temperature, but its molality won't. There's also a lot of units that are percent related. So generally down here I say percent is part over whole times 100%. If both part and whole are in grams, we call it mass percent. If both part and whole are in some unit that is a volume unit like milliliters, then that's the volume percent. And if you're familiar with the concept of alcohol being described as 40 proof or 90 proof or 200 proof, the proof is 2 times the volume percent of alcohol. So that's why 200 proof is the highest possible value for the proof of alcohol. If part is in grams and whole is in milliliters of a water solution or an aqueous solution, we call that weight to volume percent, W/V percent, which is very close to mass percent. And so a lot of times if you're just making a solution in lab, and it doesn't have to be that precise, you can just do it that way. Just if you need to make a 10% mass solution of sodium chloride in water, take 10 grams of water and add it to 100 milliliters and call that a 10% mass to volume or weight to volume, and that's pretty close to the mass percent. Now, a couple units that threw me for a long time but are really just related to percent is the concept of parts per million or parts per billion. ppms are parts per million, ppbs are parts per billion. And what you do is you take part over whole, and instead of multiplying by 100%, you multiply by a million parts per million, 10 to the 6 is a million, or a billion parts per billion, depending on which one you're trying to get to. And so they're just the numbers are just like percent, except that you're looking at it out of, not out of 100, but out of a million or out of a billion, so that smaller amounts show up in more easily readable numbers. This is a figure here from the Masterton text talking about how to make a solution. This is a solution that's being made by diluting a sample. And so they tell us here that we have 50 milliliters of 2 molar copper sulfate. This is called a volumetric flask, right? Or a vol flask. Vol flasks are quite expensive. They're measured pretty precisely. It has a line right there that you can just barely see. That is exactly when you have 1 liter in this one at a certain temperature. So we take 50 mils of our 2 molar copper sulfate and we add it to our flask, and we add water to it just up to the top, and then we very carefully add water up to the top, oftentimes shaking the flask between additions so that we get all the air out of the solution, get the solution mixed well. But you want to get it so the meniscus is just exactly on that line. Now, what concentration would this solution be? The dilution equation, M1B1 equals M2V2, is one you should really be experienced with, you should be practiced with. If we start off with 2 molar copper sulfate and we have 50 milliliters of it, we don't know what the new molarity is, but we know that we've got 1,000 milliliters of solution, and I'll put a decimal point there. That's a pretty exact number. So our new molarity, flipping the equation around, is going to be 2 molar times 50 milliliters divided by 1,000 milliliters. Milliliters and milliliters will cancel out. So 2 times 50, of course, is going to be 100. Divide that by 1,000, and you're going to get a 0.1, and I would say 0.100 molar solution is the concentration of that solution. Another concentration unit I forgot to type on here is mole fraction. We use that with gases mostly. It's just part over whole, where the part is moles of whatever component you're looking at over total moles. And if we'll say this is moles of A over total moles, then we represent that as X sub A, or the curvy Greek letter X, which is called chi sub A. That's what mole fraction looks like. If you're having to do problems where you convert from one solution to another, this table is a handy thing to let you think about how to do that. You know, if you're starting off with mass percent and going towards something else, like say parts per million or molarity or molality, you would assume initially that, say, maybe you got 100 grams of solution, and you can go forward from there. You might also need to apply density. The density of this solution might come into play. With those, but that I always think that's a good hint. That's again from a different book. Now there is something that we talk about called the Van Hoff factor, The Van Hoff factor is the symbol I, and that's the number of particles that dissolve per molecule or formula unit. So, for example, if I'm talking about sodium chloride, if I have sodium chloride and I put it in water, what I'm going to get are dissolved sodium ions and dissolved chloride ions. I is equal to 2 for sodium chloride. It has a Van Hoff factor of 2. If I have something like potassium phosphate and I dissolve that in water, I'm going to get 3 potassium ions and a phosphate ion, and in this case I would be equal to 4. If I have something like, let's say ethanol, CH3, CH2OH, and I dissolve that in water, I'm simply going to dissolve up ethanol molecules. So I is 1 in that case. So this is one, where you need to fall back on the skill of knowing the different ions that are present, knowing those polyatomic ions, and being able to discern how something breaks up as when it's in a solution. For example, if you have NaHCO3, what you need to know is that Na gives you a +1 ion, and the HCO3 is the bicarbonate ion or the hydrogen carbonate ion that just gives you 1 ion. And of course, many students will try to say the hydrogen dissolves up separately and stuff. So that I factor is going to come into play a little bit more down the road here. So now we're talking about things that are called colligative properties. And these are things that are affected by the quantity of the particles that dissolve in solution, not necessarily by the particle itself, the nature of the particle. So the molecule or the compound only matters in that how much of it's present and how it breaks up into solution. So the first colligative property we're going to talk about is boiling point elevation and freezing point depression. So what happens if I dissolve something in water is that the water boiling point goes up and the water freezing point goes down. So if here is my normal boiling point for water and here is my normal freezing point for water, this is pure water. If I put it in a solution, it goes down. This is for a water mixture, and that difference there we're going to call delta T sub F, the difference between the normal and the mixture. And then our boiling point will go up. T sub B prime is the boiling point of that, and the difference between those is delta T sub B. Now we can calculate delta T sub B and delta T sub F from the Van Hoff factor times a constant, Kb for boiling, Kf for freezing, times the molality of the solution involved. So it's a very similar formula, but you got to remember that when we're looking at freezing points, you subtract delta T sub F from the normal freezing point, the pure freezing point, and when we're talking about boiling points, we add delta T sub B to T sub B, the boiling point goes up. Now, these Kb and Kf terms here are specific to the solvent. Okay, they're not specific to the solute, the thing is dissolving, but they're specific to the solvent. M, of course, is the molality of the solute, which is the mass, the grams of solute, the moles of solute divided by the kilograms of solvent. But that's something, if you're familiar with the concept of antifreeze in an automobile engine. Antifreeze is something that you add instead of putting just pure water into the radiator, and it raises the boiling point so your car is less likely to overheat. It lowers the freezing point so that in the winter your car doesn't, the radiator and the cooling system doesn't freeze up. Another colligative property is something called osmosis. Osmosis is, we talk in terms of osmotic pressure. Now, what osmosis is, and this is very important in biochemistry, let's say we have a solution, and in that solution I have something that has a semi-permeable membrane. Now, that's something that will let, say, water molecules go back and forth, but nothing else. Now, that may sound to you like a lot of, for example, tissues in living systems. You know, a cell membrane can let different molecules pass in and out in different ways and controls it in different ways. But a cell membrane is very much something that's susceptible to osmotic pressure. Now, in this solution, so we got a solution inside and we got a solution outside. If the concentrations are the ionic strength or the concentration of dissolved ions or dissolved molecules, if those are the same, you get no movement. If they're different, then the water molecules move from the higher concentration or ionic strength to the lower one. Okay, so if this is pure water, for example, and I put into it a semi-permeable membrane with 0.1 molar NaCl, then the water molecules are going to move in this direction and try to dilute the sodium chloride solution, and they'll fail to get it to the point where it's zero. But they're trying to get the inside and outside concentrations equal to each other. Now, this osmotic pressure, which is labeled pi, that's osmotic that's equal to the molarity times the gas constant times the temperature. And if you're thinking, wait a minute, gas constant, why are we using the gas constant? Well, let's think for a second. PV equals nRT. This is our ideal gas equation. If I solve this for P by dividing both sides by V, I get P equals nRT over V. Well, what's N over V? N over V is molarity. So this comes pretty much from the ideal gas equation, so we could calculate the osmotic pressure if we knew the temperature and the concentration in molar. And I would say that we have to apply the Van Hoff factor, or we have to be aware that this is the total. So we either use I, or we make sure we got the total molarity of all ions. So if multiple ions are dissolved, then we'd have to take that into account. So for example, in this one, it's 0.1 molar NaCl. That means 0.1 molar Na plus ion and 0.1 molar Cl minus ion. So we would say IM, that's 2 times 0.1 molar, would be 0.2 molar. Or if we added those two together, we would get 0.2 molar. It's the same idea either way. Now, what you can do is you can use both of these colligative properties they can be used to determine molar mass. And you may remember back when we looked at empirical formulas, the one thing we had, we could do a combustion train type experiment, figure out what the empirical formula was, but to get to the molecular formula, we needed the molar mass. And what you'll find frequently on a lot of exams, like if you take the MCAT or the dental admission test or something like that, any test that has chemistry in it, frequently they'll harp on these ways where you can determine molar mass, because historically that was an important calculation. Now it's less important because we have other ways of doing it, but being able to do it shows that you've got a certain amount of fluency in all these different sorts of concepts and calculation skills. Alright, so what we're going to do here, this is a very common lab experiment. Students are given unknowns, and they're directed to take the pure solvent, get the temperature, the boiling point temperature of that, or the freezing point temperature of that, then dissolve the solute in the solvent and get the new freezing point, which should be lower, and calculate from that the molar mass. So we've got a student here in the first one who's determined that the freezing point is 6.18 degrees. So I'm going to write this. So that would be the TF prime, the mixture is 6.18 degrees C. We're told that the solvent is cyclohexane, which has a density of 0.779 grams per milliliter, and a pure cyclohexane has a freezing point of 6.50 degrees C. And we're told that Kf for cyclohexane is 20.2 degrees C per mol. Alright, so what we're going to try to do is figure out what the moles, how many moles had to be present. So we'll start with the first equation. First of all, what's delta T sub F? Well, it's going to be the 6.50 minus 6.18 degrees C. That's going to be 0.32 degrees C. So the temperature, the freezing point went down 0.32 degrees C. Delta T sub F is equal to I K sub F M, where M is the molal. It doesn't say in this, but we're going to assume that I is 1 in this case. It's it's a valid question. Sorry, not 2, 1. But usually you'd be told something like it's a non-electrolyte. They didn't say that anywhere here, did they? But that means that I is equal 1. So we know that delta T is 0.32 degrees C. We know that I is 1, so we'll just leave it out. We know K sub F is 20.2 degrees C per molal, and we don't have any idea what the molality is. But we can figure it out from this equation. The molality is going to be 0.32 degrees C divided by 20.2 degrees C per molal. Our units, degrees C cancels out. 1 over molals is molality. And so we have 0.32 over 20.2. So that's 0.3 divided by 20.2. So it's going to be a pretty small number. If I divided 0.32 by 10, it'd be 0.03. So I'm thinking something around 0.015 maybe. And I got 0.016. I'm going to carry all the rest of it. It's really 0.01584, so on and so forth. I'm going to carry the rest of those in my calculator, but that's the molality. Well, let's consider what we can do with that. Molality is moles of solute over kilograms of solvent. So what do we know about our solvent? Well, we know its density, and we know we had 225 milliliters of it. So what we can then say is that our 0.016 molal is equal to moles of solute. And then on the bottom, I've got 225 milliliters. And I can multiply that by 0.779 grams per milliliter. And then I'm going to have to multiply it by 1 kilogram over 1,000 grams to get it in kilograms. So if I do that, 225 times 0.779, it's going to be probably like 180, so 0.18 is about what I'm guessing here. Let's just see what we get. Let's see. Alright, I've got 225, and I am multiplying by 0.7, is it 779 or 799? 779. And that, friends, is me knowing that I might make a mistake, that I might type 0.779 when I'm in 0.799. So check that out. It is 0.779, and then dividing it by 1,000. I don't have to do anything with the ones. That comes out to be 0.175. So now I have 0.016 molal over the moles of solute divided by now 0.175 kilograms of the solvent. And if I multiply the molality by the kilograms of solvent, that's going to give me, so 0.16 molality is moles of solute over kilograms of solvent. I'm just rewriting the molality unit that way, and then I'm multiplying by 0.175 kilograms of solvent so that those cancel out, and our number of moles is going to be equal to that comes out to 0.02767 moles. If we had to round here, we would say 0.0028, but we're going to keep that till we get to the end. So we really only know that to 2 sig figs. Now, we need to know moles. We know we got 1 gram, right? So we know that if we take our mass in grams and we multiply by 1 over the molar mass, we will get moles. So molar mass is going to be equal to moles, is it going to be equal to grams over moles, which is the way I learned molar mass. And that's 0.002767 over, whoops, nope, I just turned it upside down, didn't I? That's going to be 1.00 grams that were given up in the problem over 0.002767 moles. And so when I do that, which I can just do by using the x to the -1 button on my calculator, that gives me a molar mass of around 360 grams per mole. So that's our answer for student A, doing all that. So we used the delta T sub F equation because it's a freezing point depression experiment. We then solved for the molarity in that, and then we were able to get moles by using the definition of molarity, and then we were able to get molar mass using the definition of molar mass and moles. So that's an example of that kind of problem. Now, student B in this case did an osmotic pressure experiment. So what student B did was they saw that the osmotic pressure of the solution was 0.8 .846 atms at 25 degrees Celsius, and told that the solvent is water, which has a density of 1 gram per milliliter, and the density of the solution is also 1 gram per milliliter, which is frequently a good approximation. If you have a water solution that's dilute, the density oftentimes is very close to 1 gram per milliliter. All right, so let's think about that. So I'll do B, start B over on this side. This was all A up here. All right, so we know the equation for osmotic pressure is I m r t, and we're going to assume here that I is 1. Again, we weren't told this in this problem, but we might be told that it's a non-electrolyte or something, so we would say MRT. All right, so what do we know? Well, we know that the osmotic pressure is 0.846 atms. We don't know the molarity. We know the gas constant, 0.0821 liters times atmospheres over moles times Kelvin. And we know the temperature, 25 degrees C, is 298 Kelvin, so 298 Kelvin. So kelvins will cancel out. Atmospheres cancels out. And so we wind up with 0.0821 times 298. So we got 0.846. I'll leave atmospheres in for now, is equal to molarity times 24.4658 liters atmospheres over moles. If I divide both sides by that, I get that and this is capital M molarity, not molar mass. Sorry, no, kind of drew a script M there. This is molarity. Molarity is going to be 0.846 atmospheres over 24.4658 liters times atmospheres over moles. Atmospheres cancels out. Now we'll do it there. 1 over liters over moles becomes moles over liters, which is molarity. So 0.846 divided by 24. So if it was 8 divided by 24, that'd be about a third. And so 0.08 is going to be about 0.03, somewhere around that. So 0.846 divided by the second answer here on my TI, or 24.4658. That comes out to be 0.0346 molar. And again, that's more sig figs than we probably could claim that many sig figs. Now, okay, we know molarity. So what's molarity? Molarity is moles of solute over liters of solution. Well, what do we know? We know that the molarity is the 0.0346 molar, and we don't know anything about moles of solute, but we know we had 225 milliliters of solution, right? If we slide it back up here, remember that 225 milliliters of a solvent, rather. So the densities of the water and the solution being the same tells us that the 225 milliliters is going to be the same volume for the solvent and the solution. So we're going to say this is 0.225 liters. What I did there was take 225 milliliters, divide that, multiply by 1 liter over 1,000 milliliters, and that gives me 0.225. Again, just move that decimal point over, something you should be comfortable with. So if I rearrange my equation, I've got moles of solute is equal to 0.225 liters that I multiplied across, and then the molarity is 0.0346. That's molarity. Remember, that's moles over liters, so liters cancels out, and so we're going to get 0.225 of that, so that's about 1/5 of what we had. So 0.03, so it's going to be somewhere around 0.007, I think, and I get 0.00778 moles. Now, now that I know moles of solute, remember that we had 1 gram. Remember that the definition of moles is, grams over molar mass. So that if I take the molar mass, that's going to be grams over moles. And we know from the problem we have 1 gram of our substance. We know from our calculation that we have 0.00778 moles of our substance. And so if I do that calculation, I get that my molar mass is around 100 and getting 128.53. So I would say 129 grams per mole if I were confined to 3 sig figs, which I think I am. So that's another way of determining molar mass, and gives you an example of working with the osmosis equation. Usually osmosis is used for things like really large proteins. You'll find in biochemistry a lot of times that osmosis is the tool that's used to determine the molar mass of a protein, which can be, a small protein can be 30,000 grams per mole, which in biochemistry they call Daltons. So a lot of times they'll talk about 30,000 kilodaltons. 30,000 kilodaltons in biochemistry is 30,000 grams per mole in chemistry. All right, so there are other examples of calculations that you'll see, but this is a brief overview of those, and so I hope that helps. And if you have some questions, we can go over some more of that in the live session that's coming up. All right, see you later.